This problem is in your textbook as review problem 3-3, and it reads, a rigid beam rests on in a horizontal position on two cylinders that are comprised of 2014 T16 aluminum and having unloaded lengths as shown. So those are the lengths without the forces applied. And each cylinder is 30 millimeters. What we're tasked to do is find that position where that 80 kilonewton force needs to be applied. So some x distance over from point A, so that the beams remain horizontal. In other words, and also, what is the new diameter of cylinder A? Okay. So what we're trying to basically determine is we're trying to basically say that the delta L for each column must be equal. If not, then it will not be level. All right, I have redrawn the problem as a free body diagram, and we're going to go ahead and apply the equations of equilibrium, and we're going to use the summation of forces in the y direction is equal, and we're also going to use the summation of moments at A is equal to 0. And we're going to get the force B and the force A in terms of x. So we got force B is equal to 80 divided by 3x. Force A is 80 minus 80 divided by 3 times x. We had stated that for this to be level, that the change in the lengths of each column must be equal to 0. So if we look at the strain is equal to the delta L over the original length. Okay, so if we set these equal to each other, we're going to get the strain in A times 220 millimeters is equal to the strain in B times 210. We know we can then solve for strain to find that, and the strain is going to be equal to the stress divided by E. E is constant for this one as well. So the stress that each one of them is under, so the stress of A is equal to force A divided by the area, and the stress at column B is equal to the force B divided by the area. So we already have that information that we found for FA and FB in terms of x. We put that in there. And then we let's substitute those into that original equation, which is the stress now of A divided by E times 220 millimeters is equal to the stress B divided by E times 210. Since E is the same for it because they're both made of the aluminum, those drop out, and we get stress A times 220 millimeters is equal to stress B times 210 millimeters. All right. So now let's put in the values that we had for FA and FB, and then we can cross out the diameter, or excuse me, the radius there squared, because they're on both sides. So that drops out, and the area and the pi, and we're left with an equation with one unknown, and so we can then solve for x, and in this case we get x is equal to 1.535 millimeters. Next, we want to use the new value of x that we have obtained, and we're going to then solve for the forces at A and B, and we get 39.06 kilonewtons for A and 40.934 kilonewtons for B. Since we're focusing on the column A and finding out what's happening in that column and how that diameter is changing, we need to first find the stress at A, and that's just simply the force over area, and we get 55.27 megapascals for A and 57.91 megapascals for B. Because we're just finding out column A, we now have to find what is going on with the strain at A. And the strain of A is equal to the stress of A divided by the modulus elasticity, for aluminum. So that's a lookup value. So that'll be our 55.27 megapascals, okay, divided by the 73,100 megapascals, and that gives me a longitudinal strain, okay, of 0.00030756. And we are given a Poisson's ratio at the beginning is equal to 0.35, okay? And that is equal to the negative strain latitude divided by strain longitude. And we're looking for latitude, how much it expands out. And that is going to be equal to the 0.35 times the longitude one, which we just solved for. And that gives us 0.00026, which results in a new diameter, diameter in this case, of 30.0079 millimeters.